Welcome to The Explainer. Today, we're tackling something literally out of this world, lunar and deep space missions. We're talking about humanity's ultimate journey. The sheer scale, the ambition behind these endeavors, it's absolutely monumental. And we're going to unpack exactly what it takes to make these incredible missions happen.
To kick things off, we really have to ask ourselves a fundamental question. What actually happens when we leave Earth's orbit? When we push past the safety of our home planet, we aren't just dealing with a slightly longer commute, we are facing mind-boggling distances and some of the most extreme, hostile conditions imaginable in the universe.
Okay, let's dive right into exactly what we mean here. Lunar and deep space missions are those that extend well beyond Earth orbit to investigate the Moon, planets, asteroids, comets, and the outer solar system. Because of the extreme distances and long travel times involved, these spacecraft require highly reliable systems. Out in the void, there is absolutely no roadside assistance.
Here is our mission itinerary for today. We're starting with Beyond Earth's Orbit, exploring the Lunar Toolkit, and looking at India's historic moon missions. From there, we'll be venturing into deep space, surviving the void, and finally, looking at the next frontier. All right, let's get moving.
Section 1. Beyond Earth's Orbit, Leaving Home. So the crucial point to understand here is the contrast. Orbiting Earth is one thing. You're staying relatively close to home. But lunar and deep space missions, they're entirely different beasts. They face immense travel distances and require highly complex navigation techniques. By venturing out, these outward-bound missions actually uncover the secrets of planetary formation, surface geology, atmospheric composition, and even magnetic fields. They give us the raw, unfiltered data we need to understand how our solar system formed and how it works today.
Part 2. The Lunar Toolkit. Stepping Stones to the Stars.
You'll see, we don't just dive headfirst into the outer solar system. The Moon is our closest neighbor, and it serves as our ultimate testing ground. We explore it using this escalating toolkit. Step 1 is the flyby, just passing close by without orbiting, kind of like the Soviet Luna 1 did way back in 1959. Step 2 is the orbiter, which continuously maps the surface from above. Then things get tricky with Step 3, the lander, where you're executing a controlled, soft touchdown. Step 4 brings mobility, with rovers rolling right across the surface. And finally, Step 5, sample return, which is bringing extraterrestrial material back home to Earth. It's like a giant puzzle, and every single step build a tech will eventually need for Mars.
Section 3. India's Historic Moon Missions, the Chandrayaan Triumphs.
Let's look at a phenomenal real-world example of rapid progression using that exact toolkit we just talked about. India's incredible lunar journey through the Chandrayaan program started in 2008 with Chandrayaan-1. This orbiter mission made a massive landmark discovery. It confirmed the presence of water molecules on the Moon. Then, in 2019, Chandrayaan-2 deployed an orbiter that is actually still providing valuable data today, even though its surface module had a hard landing. But, engineers learn and adapt. Fast forward to 2023, and Chandrayaan-3 achieved a triumphant soft landing with the Vikram lander and Pragyan rover.
And those Chandrayaan-3 achievements, they weren't just a national victory. They were a massive leap for global science. Landing near the Moon's south pole is notoriously tricky because the terrain is just incredibly rugged. By pulling this off, India became the very first country to land near the lunar south pole. It beautifully demonstrated highly advanced autonomous landing technology, meaning the spacecraft was literally thinking for itself during descent.
4. Just 4. That is a massive number in this context. With Chandrayaan-3, India cemented its legacy by becoming only the 4th nation in human history to achieve a successful soft landing on the Moon. When you think about the decades of global space exploration, joining that exclusive club is an absolute triumph of engineering.
Moving on to Part 4, venturing into deep space, pushing the boundaries.
So now it's time to zoom out from the Earth-Moon system and look toward Mars, Venus, Jupiter, and interstellar space. Out here, we use the exact same toolkit we used for the Moon, just applied to the vastness of deep space. For planetary orbiters, we've got missions like ISRO's Mangalyaan around Mars. For landers and rovers doing the heavy lifting on the ground, we have NASA's InSight or the Curiosity rover. For flybys, you have legendary missions like Voyager that shot past the outer planets. And for sample return, missions like OSIRIS-REx are literally grabbing material from asteroids and bringing it home. The destinations change, sure, but the foundational methods, they stay the same.
Part 5. Surviving the Void, the Perils of Deep Space.
Because while the toolkit is the same, the environment is a whole different ballgame. Out in the dark void, life-threatening engineering challenges are waiting. Now, what's really interesting here is the communication delay. Signals only travel at the speed of light. Between Earth and the Moon, the delay is about 1.3 seconds. That's a slight pause. But deep space? That delay stretches from several minutes for Mars to several hours for the outer solar system. You simply cannot remote control a spacecraft with a joystick. If a problem arises, by the time we even see the warning on Earth, the probe has already been dealing with it for an hour. So autonomy isn't just a nice-to-have, it's survival.
And they really need that autonomy because the hazards out there are terrifying. Outside the safety of Earth's magnetic shield, deep space probes face extreme thermal conditions. We're talking massive temperature variations from intense heat to freezing cold. They're constantly bombarded by a lethal radiation environment full of solar particles and high-energy cosmic rays. Then there's limited power. As you get further from the sun, your solar panels capture less and less light. And finally, navigation accuracy. In deep space, a tiny microscopic trajectory error at the start of a journey can compound over millions of miles and cause a total mission failure. No pressure, right?
So how do we actually pull this off? Through absolutely ingenious engineering. To survive the radiation, we use radiation-hardened electronics. To handle the temperature swings, we build advanced thermal control systems. For power when the sunlight fades, we rely on RTGs, radioisotope thermoelectric generators. And because we can't be there to fix a glitch, spacecraft carry redundant onboard computers. Literally, if one gets fried by a cosmic ray, the backup instantly takes over to save the mission.
Which brings us to our final section, Part 6, the next frontier. Where do we go from here?
Surviving the void is incredibly tough, for sure, but the payoff is tremendous. It paves the way for everything from discovering valuable minerals to supporting actual human settlements beyond Earth. The immediate future is packed with a new era of global collaboration. NASA's Artemis program is focused on a human return to the Moon. ISRO and JAXA are teaming up for LUPEX, the Lunar Polar Exploration Mission. ISRO is also looking ahead to the Gaganyaan follow-on missions for future Indian human exploration. And internationally, plans are well underway for a massive Mars sample return mission. The roadmap ahead is absolutely packed with action.
To wrap things up, I love this quote. These missions continue to push the boundaries of engineering and scientific discovery, contributing significantly to the future of space exploration. Ultimately, lunar and deep space missions aren't just about exploring rocks. They force us to invent advanced robotics, precision navigation, and highly reliable systems that end up pushing all of humanity forward.
So, knowing the extreme, terrifying challenges of the void, and knowing the vast engineering toolkit we've developed to survive it, where should humanity venture next? Should we focus entirely on building a permanent lunar base? Should we rush straight to Mars? Or maybe aim for the asteroids? The possibilities are infinite. Keep your eyes on the stars.